Hi, welcome to this lesson on calculus. What is differential calculus? Let's have a look at some of the applications of calculus. Now, in the real world, we can often model phenomena using an appropriate function. One of the main uses of the applications of calculus is to find either the minimum or maximum value of a given function by using an optimization technique by means of finding what we call the first derivative of the function with respect to the appropriate variable, and then setting that new function equal to 0, the derivative function. Now, this all looks a little confusing at first because it's a whole bunch of terminology without actually seeing it, but that's not the point here. The point here is to just get an overview of the applications before we develop those necessary tools, just so we get an idea of exactly what are we deep diving into when it comes to calculus. So we'll see why this is the case once we've developed those concepts as said. But for now, let us look at an example to get an idea of why we need calculus in the first place. The fuel used in a motor vehicle can be modeled by the following function. Okay, so f of v is 9/160 times v squared minus 9v plus 367.5, where v is given as the traveling speed in kilometers per hour. So f of v, this is the fuel that is consumed by the vehicle when you are driving at v kilometers per hour. We can calculate the optimal speed to travel to use the least amount of fuel possible. Now, I don't have to explain to you why in this current situation it's important that we pay attention to things like this, especially with the petrol prices being as they are, as high as they are now. So it's even more important that we know how to use our fuel very economically well. So firstly, we can actually visualize what this function looks like on the Cartesian plane. Like anything in mathematics, the context of the question is important. We are working with speed and fuel, both of which make sense to be positive values only. You don't want a negative speed or a negative fuel consumption in terms of your amount. It doesn't make sense to say that you used negative 3 liters of fuel when you drove. It doesn't make sense to say you drove negative 10 kilometers per hour. So if you look at the function, we look at the positive x-axis, which I'll call v, which is my independent variable, which determines the speed. And this is in kilometers per hour. And then my fuel consumption in liters on how fast I'm driving at a certain speed. Now, that function we were given is a quadratic function. And because of the sign here being positive, we know it has a minimum turning point, essentially a smiley face. Okay, so if we sketch that function, we see that there's a turning point here. And that turning point is given by AT and 7.5. And how we find that turning point can be used, or how can we find that turning point? Well, for the quadratic function, we sort of know that the turning point, the x-coordinate, is given by negative b over 2a, where you have ax squared plus bx plus c equals 0. But have you ever pondered to ask yourself, how did we actually know that? Where did that come from? That actually comes from calculus. And we'll actually see why once we develop the tools of calculus, how we actually got that formula. So that's really cool and interesting. But essentially, if you look at this function and you interpret it from context, that is the key thing here in maths. We're not just trying to force feed and tell you to memorize what functions look like and all that. We're trying to explain to you what the context that the function is saying to us. This is saying that as you drive your vehicle from 10 kilometers, 20 kilometers, 30 kilometers per hour, all the way up to 80 kilometers per hour, the amount of fuel you start using is quite high, but the fuel that you start using as you increase your speed starts to stabilize and go down a bit. Then it reaches a turning point, a minimum value. At 80 kilometers per hour, you're using roughly 7.5 liters of fuel in the long term as you're driving. But if you apply more speed after that, you see that your fuel consumption starts to increase again. So if you're driving around a constant speed of around 80 kilometers per hour, you'll be using the least amount of fuel possible, around 7.5 liters, depending on that vehicle that has that equation for its fuel consumption. But from the graph, we can see, the minimum value of that coordinate is given by p 80, 7.5. Essentially from the context, that means that the fuel that you're using, as we said, it starts off at a high fuel start from an early speed, and it decreases as we increase our speed up until around 80 kilometers per hour. At this point, we use the least amount of fuel, around 7.5 liters. But then as we increase our speed over 80 kilometers per hour, the fuel that we use begins to increase again. So essentially, how does calculus help us here? Well, as we'll learn, we can use the first derivative of the function and set it equal to 0 to find the optimal speed. And that's essentially what optimization problems are all about. It's about taking the function, finding the first derivative, setting it equal to 0, and we will see why we have to set it equal to 0 as well. You've got to ask yourself those questions. Why are we doing this all the time? What is the actual meaning of it, and how did we get there? But that'll all be explained once we develop the tools. For now, we can see the direct application of the tools. So essentially, from this function f of v, we take the first derivative, and we will see how this is done. But essentially, if you do the calculations, you see you get v equals 80 kilometers per hour, which is that minimum turning point. So don't stress on this equation for now. We will develop the tools to get there, but we can actually see that the tools do work, which is very nice. So using the first derivative allows us to find minimum or maximum points on more complex looking functions. And this is one of the most amazing powers of calculus. So now that we have the idea of what calculus is all about and what we can do with it, we can start developing the tools to start using calculus. By this, I mean we'll go through, first of all, what are cubic polynomials. We'll have a look at the factor and remainder theorem for polynomial functions, because that'll be crucial for us later on in understanding how to sketch cubic functions. The concept of a limit of a function, that's really important in calculus, and hand in hand that goes with the derivative of a function. And then we'll look at the derivative laws and hence apply applications to them using optimization. Okay, so that is the field of differential calculus that we'll be deep diving into. And yeah, we will do some more examples and develop the tools necessary. Okay, I'll see you in the next one.